Okay, so in the preview activity, we had this function g here, and we saw that specifically, let's talk about as x gets as close as we want to 0. As x gets as close as we want to 0, we see that g, the function g, is getting as close as we possibly can to a value of 4. Now keep in mind that x is never equaling 0. We're just getting closer and closer and closer to 0. And if we take that concept to a little bit higher level, what we're going to need here is this is the notion of a limit. A limit means that we're getting as close to a number without actually equaling that number. We're getting closer and closer and closer. So we have this definition of a limit, which is a little bit wordy, but here it goes. It says, given a function f, a fixed input x equals a, and some real number L, we can say this: f has a limit as x approaches a. And the notation we use to write this is we use this notation here. And the way I actually read this notation, I say the limit as x approaches a of f of x is equal to L. And this is what limit notation is all about. And I want you to keep in mind something here, that when we're taking the limit as x approaches a, it needs to be of some function. There needs to be some function that we're taking the limit of. Now, this is provided that we can make f of x as close to L as we like by taking x values, which are very close but never equaling a. And if we can't make f of x as close to a single value as we would like, as x approaches a, then we have a situation where the limit does not exist. And we'll go back and take a look at that. That was also in the preview activity, but we'll take a look at that in a few, maybe a little bit later on. Okay, so this is going to bring us to our first example of section 1.2. And we're going to consider this graph from the preview activity, and we can make the following observations. So let's just make sure that we're all in agreement about this. The first observation says that the limit as x approaches -1 of g of x, there's our argument, is equal to 3. So as I get closer and closer to -1, as x gets closer and closer to -1 without actually equaling -1, then we can say that the output is getting closer and closer to 3. The next statement that we can make is we say the limit as x approaches 0 of g of x is equal to 4. Well, that's the one we just talked about, so hopefully we're in agreement there. The next one, we say the limit as x approaches 2 of g of x, again there's the argument, is equal to 1. So let's look and see what happens. As x approaches 2 without ever equaling 2, g of x is getting closer and closer and closer to an output value of 1. Now notice that g of 2 is actually undefined. There's a hole in the graph here, but we're never equaling 2, so it's okay to say that the limit does exist here. It's getting closer and closer to 1 because we never actually equal 2. But look what happens when x approaches 1. As x approaches 1, we can see that something's happening with this graph. There's a discontinuity in the graph. The graph actually jumps here. So as I approach 1 from the left, I can see that it's the limit as x approaches 1 from the left has a value of 3. But as I approach x from the right, we can see that it has a value of 2. And because those two values don't match, we really can't say that the limit exists here. So the limit as x approaches 1 of g of x simply does not exist. And I want to draw attention to the fact that we didn't put an equal sign here, because we can't say it's equivalent to does not exist, because that doesn't make any sense. So we just say the limit as x approaches 1 of g of x does not exist. Okay, so there are 3 ways to answer the question, does f have a limit at x equals a? The first way that we're going to do it is to reason it graphically. And that's what you did in the preview activity. You look at the graph and you determine the limits from a graph. The second way that we're going to be doing this is we're going to evaluate the function at a sequence of inputs that approach a on either side, which is just a fancy way of saying we're going to be using our calculator to find this table of, we're going to be using the table of values on our calculator, which we'll show you in the next video. And then the third way is we're going to use an algebraic approach of the function, and we're going to try to figure out if the limit exists using algebra. And you're going to see those things in action in this next example that we do.